All right, so good afternoon once again. I will do some very elementary examples in real space for renormalization, of the renormalization group. So the elementary examples I will consider are two, one from classical physics, the other from quantum physics. And I will go halfway and do it for you. I will just show you and give you a flavor for it. It's not as though I will do the entire algebra and all the fireworks. I have to tell you that there is also a competing approach. It's called in momentum space. There's another approach. We will not be discussing it. So the example that I will first do, as I said, is from classical statistical mechanics. And we will take the Ising model in one dimension. So we look at the Ising model, H is equal to minus J, sum over I, Si plus 1. And this is the Ising model in one dimension. And J is greater than 0. I'm assuming you have had exposure to the Ising model. J is positive. If J is positive and if this is my Hamiltonian, then I will get ferromagnetism. So this is ferromagnetic. But if it's trying to do something, it is better, since I'm doing a real space renormalization, I have a finite system. So let me have a system in which there are n sites, and let me put temperature in already. It's statistical mechanics, so there has to be temperature. Okay, so I will write as Hn and divided by Kt. This is my Hamiltonian now. My Hamiltonian is Hn by Kt, and I will write it as minus. This is, of course, the Boltzmann constant. I write it as K sum over I, Si, Si. What is this K? K is equal to J by KBT. Just to make things simple and not keep carrying this KBT throughout. Now, what is the problem in statistical mechanics? You must get the partition function of this Hamiltonian. It is like saying in quantum mechanics, what is the problem? You have to get the wave function and the corresponding eigenvalue. You must get the partition function of this Hamiltonian. Is it possible? Answer is yes. In one dimension, it is eminently possible. Okay, and the result is also well known that there is going to be no phase transition except unless you got right at temperature T equal to 0. So the Ising model in one dimension is basically not ferromagnetic. You just raise the temperature, you get parallel. But since we are working out an elementary example to get a flavor for how the renormalization group argument goes, okay, let us do this problem. It is simple enough to do and present in about 15 minutes. So this is mine. What you do is the following. You do what is called, you take 3 sites at a time and then you group them together. Okay. So what you do is the following. The picture here is the following. Now this is the picture on the right, on the left hand side. On the right hand side will be the algebra. The picture is 1, 2, 3, 4, 5, 6, and so on. And there are many. You take 3 sites at a time. What you do is, no, not in this case. You don't take 3 sites at a time. You take the site, and at every step in the renormalization group process, you remove this. So in the next iteration, you are left with just 4 sides, since I will remove 2 n. How to remove it, we will see in a minute. Okay, so don't worry about how to remove it, right? But I'm going to remove this. And instead of K, which was the mediating interaction, between the first and the second site. This K that you see, where is this K? Instead of that, you will have a new thing called K prime. Okay. If I'm going to remove this and this need not be linked by K. It might be K by 2 for all you know, or K by 3. Any guesses for what it will be? Supposing I do this, and I ask you, and I know that you have done nothing at all about renormalization, but as I remove that K, remove the middle side, remove 2. K becomes K prime. How much would K prime be? 2 times K, K by 2, what would it be? Take a wild guess. Yes. That's a Hamiltonian. What would it be? Take a wild guess. You can be wrong. I don't expect you to be right. Anybody else would like hazard a guess?
It should be smaller. So I would like to guess. So,
Yes.
so 3K by.
So there are answers. It can be 3K, it can be K by 2, etc. You will see what happens. But the first question is, how in the world are you going to decimate this? This procedure is called decimation. So there's a name for it, it's called decimation. Decimation is one way of doing a real space renormalization group, not the only way. So we do. What you do is, you look at the partition function, because that's the operating thing. You say that for the new Hamiltonian, the partition function is going to be e raised to k prime, correct? S1, S3, right? Because S2 is aimed there. Plus, I might, I'm not saying I will, I might pick up another term and I'll call it 2G0. I might pick up an extra term. You have to allow for that. In fact, if G0 can turn out to be 0, for all I know, but I must allow for that possibility. This is going to be that is how should I put it? The partition function is evaluated. The partition function is evaluated by saying that I must take all possible configurations. This side is equal to this side, I say. Essentially, that's what I'm demanding. So let's demand that, and let's see what will happen. Let us say S1 is equal to 1 is equal to S3. That is one possibility. Both the spins are up. What would this become? This is E K prime. S1, S3 is 1 plus 2G0. Correct. What is this thing? Okay. S1 and S3 are what? 1. Okay. So S2 can be 1. Okay. So in this case, this would become E raised to 2K. But S2 can also be minus 1 because I'm coming over all possible configurations. That is what a partition function is supposed to do. Okay. Plus these 2 groups. Step 1 is now, since I have 2 unknowns here, I have 2 equations. The second equation is easily generated by taking S1 is equal to 1 is equal to minus S3. S1 and S3 are opposite sides. What would this become? Yes. Yeah, Mr. Sukhan Chamali, what is the first term? E raised to what?
Can you repeat what is S1 and S2?
What I already repeated, it's obvious.
Yes, this one only. I can't see it clearly.
What?
So I can't see it clearly because of the connection. Can you repeat it?
Who is this?
Sukant.
Why have you not told me earlier?
So no, I'm just saying the last line which you have written, which you are asking me. The S1 and S3 is.
Don't worry. Yes. Can anybody see this board? Yeah. What about you? Yeah. So tell me what is the answer. What is that? S1 is equal to 1 and S3 is equal to minus 1, what will happen here?
e raised to minus k.
Who is saying this?
Saugant. E raised to minus k dash.
K prime.
Okay.
What will I get on this side? S1 is equal to 1, S3 is equal to minus 1, this will get 0. Correct? So whether S2 is equal to 1 or S2 equal to minus 1, you will get nothing. What will I get here? Come on, at least now, Mr. Chamoli. On the right hand side. Now,
Sir,
Mr.
always 0. 1. E power 0.
What will I get?
E power 0 plus E power 0.
Yes, so what is that?
2.
Yes, correct. Is that right? So now can I solve this equation? Answer is yes. I put one on top of the other. The 2g0 cancels out. I get e raised to 2k prime is equal to cosine hyperbolic 2k. So the first equation will give you k prime is equal to half log cosine hyperbolic 2k. Put one, you get e raised to 2k prime, you get cosine hyperbolic, and then take the logs of both sides. What would G0 turn out to be? Take any one of these equations. For example, take the second equation, you will get that G0 is equal to basically k prime by 2, correct? Plus half log 2. So I think I can remove this without losing the audience now. Is this clear? So you have this. So these are called my renormalization group equations. So k prime is not equal to k by 2. It's a highly nonlinear equation. Relationship between k prime and k is highly nonlinear. G0 is also not 0. So the first thing to notice is k prime is some function of k, which is nonlinear. And the second thing to notice is that my G0 is not equal to 0. That's why I said, let us allow for that possibility that it may not be 0. Is that clear? So now you say, what do I do with this? So what I say is, you keep doing this over and over again. If you keep doing this over and over again, you get a k double prime is equal to f of k prime. It will be equal to f of k. And you try to seek two things. And that is the great thing about this. That is one of the new things in renormalization group, Wilson, Kadanoff, and others. Okay, is that a new language had to emerge. This was a new mathematics, and a new language had to emerge from this. It's called the language of flow lines and fixed points. Okay. So you try to see for the flow line of k. For example, you'd like to see how k evolves as you iterate. How will this k go as I keep doing it over and over again? This is the first iteration, so I got this equation. I do a second iteration, I will get this equation. So how will it go? So you look for the flow line. And then you look for the fixed point. The fixed point is basically that when you get f of k star is equal to k star. That what I put in here is what I should get out. Okay. So if I put a certain say k equal to half, I don't know, I don't think that makes sense. But I must get k prime equal to half. Then whatever else I do, I'll get the same number over and over again. Okay. If k is say 10 and k prime is 10, then I put the k prime equal to 10, I'll get k double prime equal to 10, I get a fixed point. So you look for the flow line and you look for the fixed point. And this fixed point for this particular Ising model, okay, Hamiltonian kind of, the fixed point must be non-zero. for a phase transition. If a fixed point is 0, it means that your J is going to 0. And if it is going to 0, it means the interaction is going to 0 as you renormalize, which means that there will be no interaction, which means that there will be no magnetism. But if the fixed point is going to a finite number like 0.5, say, 0.6, or 10, or 20, or whatever, then it means that there is a non-trivial fixed point and there is going to be a phase transition. That is the interpretation of the renormalization group. So what happens in this case, and you can show this, okay, is that if k is 10, k prime will be 9. And then when k prime is 9, it will become 7 or something. So the flow line is such that it will go to 0, which means that there is the fixed point is 0. Now let us see this. One is that if k is equal to 0, cosine hyperbolic of 2k is equal to 1, log of 1 is 0, so k prime is equal to. If k is equal to infinity, k prime is equal to infinity. That is not hard to see. So only trivial fixed points need to be this and this, k equal to 0 and k equal to infinity. But you might say, what about somewhere in between it might happen again? How do you know it doesn't happen? Okay. So I can give you some arguments for this, and I can give the algebra is very simple. What I say is if you define a rho which is equal to tan hyperbolic k, tan hyperbolic k, work out this algebra. You'll be able to show that tan hyperbolic of k prime, which is rho prime, is equal to tan hyperbolic square. So what I'm saying is this looks unmanageable in trying to understand this problem. But if you are smart, take rho to be equal to tan hyperbolic k, put it here, doesn't matter. And define a rho prime as tan hyperbolic k prime. So you get tan hyperbolic k prime is equal to half log cosine hyperbolic 2k. And you can show that tan hyperbolic k prime is equal to tan hyperbolic square k. So this is something we show. If you show it, then you are home, because what you will then say that tan hyperbolic x is always less than 1. Correct? It goes between -1 and +1. What is the plot of tan hyperbolic x from -1 to +1? How does it look? Tan hyperbolic x, if I had a tan hyperbolic x, how would it look? It goes like this. Maximum value is 1, minimum value is -1. Correct? So if tan hyperbolic of k is 0.7, it is like 0.7 square is 0.5. Then you put 0.5 square. Is that clear? You will certainly get k prime is less than. Successively this will happen. So there is no phase transition in one dimension. Okay. That is for a classical system. Any questions? I'll wait for a minute and I will drink of water or something.
So,
Yes.
Sir,
Please identify it.
this is Prithvitosh.
Yes. Mhm.
We saw there are two fixed points, one at 0 and one at infinity, both of which are trivial. And at 0, that implies there's no interaction and hence there's no phase transition. But at infinity, what happens at like the fixed point at infinity though? Then the k, and then the Hamiltonian is non.
Not a meaningful one at all. That can also be demonstrated, but forget the infinity point. Yes. Infinity point doesn't mean there's a phase transition. Forget the infinity point.
Okay.
So this
It's not
is
a
John.
answering a question. It's just that I'm not. We don't have the time to get into that nitty-gritty of that one small mathematical point about how to interpret the infinity.
So this is John. I have a
Yeah.
question
Okay, sir.
regarding how the flow line is constructed.
Huh?
So I have a question about how the flow line is constructed.
What happens is
So
you take this, go to your computer, take any value of k, 10, any value you want. Okay. You'll get k prime on a calculator or computer. Put that, suppose you get 7, put that 7 here, you'll get 5. Put that 5 here, you'll get 4. So with every iteration, you'll get a new value of k. By iteration, it means this is like a Newton-Raphson, whatever it's called, simple iteration. You'll get a new value of k and it will actually converge to 0. Any finite value start at 100, 2000, 20, they will converge to 0. That's what I meant. That is what I was saying. Right.
yes.
Okay.
So and you showed of those composition of those functions, right? F of k. So where is that used?
Mm-hmm.
So you said we'll decimate it repeatedly, but have we used that anywhere in this calculation? We just done it once, right?
You can do it over and over again. Now you have these sides. Take these two. Remove this. That is what you are essentially doing. When you are repeating it, you don't have to do this. Keep this. You can keep this mental picture in mind. If you do it once, you have decimated once. You have done it twice, you have decimated twice. Until you are actually, when you do it many, many times, you have only a sparse lattice, and with the interaction term not increasing or staying constant, but going to 0.
Yes.
That is what it is.
Sir,
Who is
this is
this?
Chandrasekhar.
Yes.
Chandrasekhar, how do we know that at the subsequent levels, the
Huh?
function f remains the same? How do we know that at subsequent levels, the f remains the same? So f of k.
Suppose this, that algebra which got e raised to 2k prime plus 2j t0 is equal to whatever, that remains the same. So the function has to remain the same because I am decimating in the same process, same way. This procedure, how is this procedure effected? The procedure is effected by saying that e raised to 2k prime, e raised to k prime plus 2g0 is equal to e raised to 2k plus e raised to minus 2k. Therefore, e raised to k double prime plus 2g0 prime is equal to e raised to 2k prime plus e raised to minus 2k prime. That's all that is happening.
Okay.
So it has to be the same. Okay. All right. Now I So quantum okay, but I won't say statistical because we have temperature T equal to 0. When I did the 3-side problem and the n-side problem, we were just basically doing temperature T equal to 0. And I said, let us calculate the total electronic energy. I said, integrate from minus 2T to mu. There was no Fermi function there. So I will remove the statistical and say quantum mechanics. Let me put it more clearly at T. How to do? What am I? How to do this problem? Okay. So this problem basically, what I'm after is what happens to the system if it is disordered. I will not put disorder as yet, but I will just tell you how the procedure works for an ordered system. So I have 1, 2. Well, the picture is on this side. 1, 2, 3, 4, 5, 6. This is 3. This is 4. And now what I do is I group. I'm doing a real space normalization group in which I will group things. This whole thing is 1. I'm not decimating. This whole thing is 1. And I say I'm going to replace this by another site called A, and I'm going to replace this by another site called B. Here, what is the thing which connects the two? A matrix T. A transfer term which is called T. A hopping term which is called T. So it is the transfer term that I'm looking at. And that transfer term is going to get renormalized to T prime. Let me take the case where mu is equal to 0. Without loss of generality, mu is equal to 0. Therefore, for a 3-side problem, the ground state is minus root 2t, then the first state is 0, and then it's plus root 2t. This is the picture. So what I do then is this is A and this is B. Okay. And I say, okay, my T prime, CA dagger, CB. Something like this. Okay. CA dagger acting on A and CB on B, okay. Because CB is another lattice, is this lattice, and CA is this lattice. This will be equal to say minus. So let's not worry about the sign T. You'll get basically you get this is to be equal to C. Something like that. I need this connection to T, say into C3 dagger. C4. Can I just rewrite this? I'm not. No, I've not done a good job here. I should say that this is equal to C3 dagger. So it's basically going to connect these two. Now, this procedure in which I try to relate T prime to T is described. It's described in a somewhat pithy or simple, but it is as well described as you can see anywhere at all. This procedure to do it was first actually thought up by us based on what our reading of Wilson's paper on the Kondo problem. And this procedure is in the Journal of Physics C. This is a 1984, not 1985 paper by 3 people. One is Guru Nandan Bhatt and myself and Christopher Rao. So, it is, and I think I mailed the paper to you. The procedure is described in section 2. In that paper, it is for a disordered system. You can set the epsilon of the disorder to 0 and carry out this algebra. Let me give you an understanding of how this algebra is to be carried out. So what you do is, you look at that quantity over there, and I have to just revert to my notes for a minute because I don't want to make a mistake. So the interpretation, if you use first order perturbation theory, the interpretation is as follows. Okay. You look at this and say this T. This of course will be T prime. So T into C3 dagger, C4. What is the state it's going to act on? The C3 dagger is going to create something, and C4 is going to destroy something. So we say that the C3 dagger is going to create something from a state which is the ground state of a single occupancy system. Let me take this down and then I will explain the procedure to you. So this thing and this thing, they are going to act on different states. I don't know if you have heard of things called direct products. So this is basically a direct product algebra. But if you have not heard of it, don't get scared and run away from this discussion. Okay, don't fade out from it. Then it's basically you take the C3 diagram. The procedure is you take the C3 diagram and you make it operate on a state which is a single occupancy state. We take the C3 diagram. What would be the single occupancy state? Ground state. It would be R 1 0 0 plus 1 by root 2 0 1 0 R 0 0 1. What will it create? It will create a two occupancy state. So on this side, what you take is a double occupancy state. What is a double occupancy state that you have? It will be basically R 1 1 0 plus R 0 1 1 plus 1 by root 2 1 0. This would be the double occupancy. Go back to your notes. That the thing that I raised in the beginning, I had to do it so that I could remind you what the double occupancy state is. This is the double occupancy state. This you will operate on. Now you do one thing so that you can be sure that you can carry it through when you read the second section of this paper. Operate this. Tell me what the answer is. I will wait for 2 minutes so that I will let you operate. Or evaluate that thing.
Sir,
Yeah. Tell me.
I don't understand what's happening.
I have to relate t prime to t. Okay. So the way you are taking the partition function to relate, like in statistical mechanics. So what you do is you look at what is relevant for t. It is what are these? There are two sides. There are two cells. There is one cell. There is another cell. I want to replace it. Okay. What connects these two cells? The side 3 and the side 4. Okay. So I try to evaluate what is C3 dagger C4 acting with this T. This justification for this you will find in section 2, but at least in some, how should I say, hand waving sense. One can see whatever one is trying to do. One wants to do this, but I need some states. No, this is an operator. I mean, this will make no sense. What is meant by relating T C3 dagger C4 to something like T prime CA dagger CB? You can't really do this. What is meant by relating operators? So you have to take some states here. So I'm saying you take a state here. If it is a C3, it's a state which creates. The ground state is this. Let it create. Therefore, on this side, you have a two-particle state. Otherwise, this whole thing will go to 0. So what happens is, basically, if you want to relate T prime to T, one has to write the whole space, all possible possibilities, and evaluate it. I'm taking a small subspace of it and relating T prime to T in that small subspace. It's a big word. It's a big word. What I'm asking you to do right now, Mr. Prithviraj, is to just evaluate it. Just do this first. We will see about the justification later.
Okay. Okay, sir.
Just the first two terms, it will happen. Third term would be 0 only because it is already.
Yeah. So what you're saying is now, what would it be? I want somebody in the audience. If I take C3 diagram and operate on this, First of all, I want to be sure whether you understand how second quantization works, how creation and destruction operators work. So this is just a test to see if you can do this. I'm not saying that I've explained the procedure. See, supposing I have C3 tag and I operate on this, what will I get?
So 101.
101 with a minus sign.
Yes.
Correct. Okay, because first I have to create 3 and then 1. Okay, what will I get here?
-1/2,
So
0, 1,
0, 1, 1.
What will I get here?
So 0.
0. Now evaluate the inner product. So this is a 2-particle state. On this side, I need a 2-particle state. I can take the whole subspace of all possible states, but all of them will give you 0 if they are not 2-particle states here. If the 3-particle state, you will get a 0. If there's a 2-particle state, there's a 2-particle state. Take the inner product.
-1/2. -1/2.
I want somebody else also to evaluate it. But just pay attention over here. You have this 101. Where is 101? Is over here. So you get 1/2√2. Right? Into 1 because 101. What about over here? This 011. Is there a 011 here? Here there is 0. So what do I get? -1/2√2. Correct? So you just have to sum this up. This is simply equal to -1/√2. Correct? That says that I have T prime is equal to T/√2. But that is not taking into account the other term, which is CB dagger CA. Make the Hamiltonian perturbation, you must take CB dagger CA. So that will give you another 1/√2 term, and you simply get that T prime is equal to T/2. So this is the operational way in which I'm going about. What is the background to it? The background to it is this picture. There are 2 cells. Out of these 2 cells, I want to make 2 sides. Picture 1. Then how do I effect it? I have to take T prime CA dagger CB and I have to take T C3 dagger C2. But I have to evaluate it in the whole subspace of all possible wave functions. Out of all of them, I'm saying the only relevant one is this and this. You try other ones, you'll get some answer. Okay, but if you're looking for the ground state of this problem, on the right hand side, you must have a ground state. Okay, of a single particle state, and that's only this is allowed now. On the left hand side, you must have the ground state of a 2-particle orbital. I don't think you can do anything. Everything else will be 0. And you simply have that T prime is equal to T/2. In fact, minus T/2. You will get a minus. No, you will get plus T because the other one also gives you a minus. You get T/2. Okay. Then T double prime. So eventually, if you look for the flow line, it says that in one dimension, there is a tendency towards localization. There is no phase. In the sense, in one dimension, there are one-dimensional phase transitions, in which zero temperature phase transitions, which are called quantum phase transitions. This one says that all states are going to get localized. that is the idea behind the renormalization group for real space and for a quantum system. The quantum system is necessarily very complex to do. It's not as simple as the one that I showed you for the classical system. And it requires a certain amount of effort and knowledge of first order perturbation theory and second order perturbation theory to do. That is indicated in section 2 of this paper. So you cannot get around not reading that part. Because if you don't want to read it, it's up to you. It's perfectly your choice. But if you'd like to understand how the argument goes for renormalization group for quantum systems, it is a must. You have to do it. Then you can also ask the other question: is there an analog of that G0 in this quantum system? That is to say, if I have H prime, is this H prime plus H0 is equal to H? Is that what I am doing or not? That's all. And the answer is yes. That G0 is then, just as in the earlier case, in the case of the Ising model, here in this case, it gives you the answer very close to minus 2t by pi for the ground state of the half-filled system. You remember we did this minus 2t by pi. If you evaluate this dg0, you get an answer very close to this. Answer is yes. Not that I have explained it. I've just given you some flavor of how this arguments for the normalization group work. Any questions? I think it's hard because things are not clear to you. Okay. Please read section 2. Then you may have a few questions. Okay. The other thing is, of course, what is the relevance of this to disordered systems? The relevance is that when this paper actually addresses that point. If you have a small disorder, what happens to the renormalization group equations? That's why I took up this lecture in this particular course. If I was doing solid state and I had to do a renormalization group, I would just do the ordered case. I would stop at that. Okay. Thank you very much. Please, okay, there's some remarks that I want to make. Well, this is certainly inspired by the work of Ken Wilson, who got the Nobel Prize. Actually, this is all a series of papers we started around 1970, 74, 76. At Cornell University. It was inspired, and it was certainly pushed by this work, earlier work by Vijay and Kavanaugh. And of course, Wilson got the Nobel Prize in 1982 for his work. Now, why am I telling you this history? Because there was an explosion of activity regarding scaling and renormalization group inspired by these studies in statistical mechanics. And the excitement had to do with two things: that there is a deep and useful connection between statistical mechanics and quantum field theory, and I would say there's a deep and useful connection quantum field theory, classical statistical mechanics, and quantum and algebra and many-body quantum systems. Once you saw this connection, I think a lot of people got very excited, particularly the theoretically inclined people, and put a lot of effort into this. into this work. And of course, this work grew. And then, of course, it reached a small stalemate of sorts after that. Okay, thank you very much. Just all right. I will take the attendance. Don't leave. Wait, I first take the attendance and I will take.